Thank you for the nice introduction. My name is Sankat Timsina, and I'm from University of Victoria, Canada. Today I'll be presenting our recent work on resonant squeezed light from photonic Cooper pairs. So this is a familiar Raman scattering. The figure on the left describes the Stokes event, where the incident laser is scattered into the red-shifted Stokes photon and emits a phonon. The figure on the right describes the anti-Stokes process, where the laser absorbs the phonon and emits the blue-shifted anti-Stokes photon. Now, however, when the same phonon that is excited during the Stokes process is absorbed by the another incident laser, then we have Stokes anti-Stokes correlated Stokes anti-Stokes photon pairs. These photon pairs are what we call the photonic Cooper pairs. Now, this photonic Cooper pair formation mechanism provides an additional mechanism for four-way mixing, and we also note that this Cooper pair formation can occur both at phonon resonance and away from the phonon resonance. The one that occurs away from the phonon resonance, we call it the virtual Cooper pairs. Now, so far, the studies on the generation of photonic Cooper pairs have focused on the short evolution time in free space. So we are interested in understanding what photonic states emerge when these correlated photon pairs are allowed to evolve inside the silicon waveguides or photonic devices. So we developed a model for phonon-mediated photon-photon interaction in which the Hamiltonian HR describes the Raman scattering Hamiltonian under parametric and rotating wave approximation. So in taking the parametric wave approximation, we assume that the laser is approximated by the classical wave. Here, the operators BS and BS describe the Stokes and anti-Stokes mode, whereas the operator C describes the phonon mode. Small q is our dimensionless Raman shift, and our figure of merit for the photon-phonon interaction is eta, which plays a crucial role in our theory. Interestingly, the eta plus minus appearing in the Hamiltonian can be tuned by the laser intensity and the frequency of the laser. To solve this Hamiltonian, we adopt exact diagonalization with the number method, where the technique is to rewrite the Hamiltonian in the form where this V is the column vector representing the particle-antiparticle operators. We obtain an exact diagonalized Hamiltonian where the canonical transformation mixes our photons and phonons with antiphotons and antiphonons. So we get a new set of operators alpha, which create the hybrid photon-phonon excitation that we call Ramanitone. This is a Ramanitone dispersion for two different values of eta, 0.1 and 1. So we observe some interesting properties. The black line is the Ramanitone 1 with mode frequency omega 1, and it is completely decoupled from phonon. It's a pure photon mode, whereas the other two Ramanitones, they are the hybrid in a sense that they mix photons and phonons with antiphotons and antiphonons. Now, we also observe that for small values of eta, the hybridization is significant only close to the resonance, whereas for large values of eta, the hybridization occurs for the wide range of Q. So from the core effect that is estimated from the dispersion and for achievable pump power on chip, we estimate the value of eta to be 10 to the power minus 3 in silicon photonics. To understand the origin of squeezing, we note that there is an interesting symmetry in our Hamiltonian, where this NS, NAS, and NC are the number operators for the Stokes, anti-Stokes, and phonon mode. As a consequence, this occupation, they oscillate as a function of time. So at a particular value of evolution time or the waveguide length, the number of phonon NC goes to 0, and And this is a condition of resonant squeezing. When NC goes to 0, the Stokes and anti-Stokes photons are paired up, and this leads to the maximum squeezing, as we'll see shortly. To quantify the amount of squeezing, we define the generalized quadrature for our two-mode Stokes anti-Stokes photon pairs. And the degree of squeezing, this is degree of squeezing as a function of time for two different Q. The red line is at a phonon resonance, whereas the blue line is for Q away from the resonance. So we observed this interesting oscillation, which is a consequence of the coherent population transfer between phonons and photons. The black line here is a quantum noise limit. So for each value of Q, we know that there is a value of evolution time or the waveguide length that maximizes squeezing. So we plot the squeezing as a function of different Q, the Raman shift, for three different values of evolution time. And we observe that the maximum squeezing happens for the resonant condition at phonon resonance. So this, we predict up to 28 decibel of squeezing for the silicon waveguide that's approximately 8 millimeters long. Now for other values of Q, other values of the resonant length is different, and as a consequence, they have this local maxima as a function of Q. So to summarize, we developed a non-perturbative theory for the phonon-mediated photon-photon scattering based on the concept of Ramanitone, which is a hybrid photon-phonon excitation. Our theory shows that Raman scattering of phonons act as a generator of two-mode squeeze state of light. And when we apply our theory to the silicon photonics, we predict up to 28 decibel of squeeze light. And this maximum squeezing occurs at a length that satisfies both the resonance squeezing condition, that is when the phonon number goes to 0, and at phonon resonance condition. You can check out more about our work in this archive paper we just published. And I want to thank my supervisor, Rosario de Souza, my co-authors, and there's interesting experimental work going at the University of Victoria in Professor Alex Brollo and his group. With this, I want to thank you for listening.